The form booklet provides the derivatives for a whole bunch of different functions, and on top of that you're expected to know off by heart the derivatives for some other functions as well. But isn't it unsatisfying when you have to use things without understanding where they come from? So let's solve that issue in today's Prove It video. So these are the 6 derivatives we're proving in today's video. I must admit, when playing this video I was unsure if these derivatives were individually worthy of their own entire Prove It video because they're individually quite quick to do. But I thought I'd get around that issue by just doing all 6 of them in one video. So hopefully you enjoy what we're taking a look at here today. It's also worth noting that normally at this stage of the video I'd give the usual warning for the Prove It series by saying, ooh, don't worry about knowing this stuff for the A-level exam, but I'm going to make a bit less of a big deal of that issue here today because it could be argued that this stuff is on the borderline of being stuff you could be asked in the A-level exam. I'm not saying you need to know the stuff off by heart, so I'm not expecting anybody to have to come back to this video at a later stage and sit there learning by rote, line for line, everything we're covering here, but it's more of a case of I'm expecting people to be familiar with the techniques we're using and to be comfortable with why we're using the techniques in the specific scenarios that we do, because admittedly, although these things are still very algebraic, they're a lot less algebraic than a lot of our other Prove It videos, and therefore the level of difficulty is more in line with the level of difficulty of an A-level exam, if not actually easier in some cases. So being comfortable with what we're doing rather than learning off by heart the steps is arguably important. Anyway, with that said, what are you expected to know in order to be able to do these proofs? Well, I'm expecting you know the derivatives of sine of x, cos of x, and e to the power of x. But wait a minute, some of you are looking at that going, wait a minute, that's cheating, just being able to quote what those derivatives are as part of proving something else. Well, it's because I already have a video released earlier this week going through differentiation by first principles for these functions. So do take a look at that if you're interested. However, I must admit, I did take a few liberties when it came to talking about evaluating the limits at the end, and that's just because that was a maths tutorial video focused on what you need to know for A-level exams, and so therefore I was focused on just what you need to know for those exams, which didn't include in-depth knowledge of what's happening with those limits at the end. But therefore I probably will make a Prove It video, or can we do that video at some point in the future, covering what's going on with those limits. So stay tuned for that. You also need to know how to do these differentiation techniques, chain rule, product rule, quotient rule, and again, you can prove these things from first principles, and I'll have Prove It videos for those things, so check those out. Another couple of techniques we're going to be using as part of this is we'll be using implicit differentiation on a couple of occasions, and then also, because trig's involved, trig identities will get involved at some point. Cool! Now that we've got all that out of the way, let's get on with doing our 6 proofs, starting with the derivative of tan of x. Tan of x, of course, can be rewritten as sine x over cos x, which is good because it means we've got a fraction, which means we can apply quotient rule to it. So let u equals sine x, let v equals cos of x, and differentiate them both. Of course, sine of x differentiates to cos of x, watch out, differentiates to minus sine of x, and therefore we can place those 4 things within the structure of quotient rule, like so. Of course, that's your du over dx times by v minus the u times by dv over dx, and because our dv over dx already has a minus sign in it, we end up with this minus minus situation in the numerator, which could be, of course, replaced with a positive sign. Of course, we've still got the v squared situation on the bottom of quotient rule as always as well. And then this is actually a perfectly valid derivative for tan of x. It's just not in the format we used to seeing because it's not been fully simplified. So therefore, that's what we're going to do now. There's a couple of different ways you could go about that. One way would be to split the fraction into 2 mini fractions using the plus that's in the numerator. Of course, anything divided by itself is 1, so that first fraction on the left simplifies to 1, and the fraction on the right as sine x over cos of x equals tan of x, sine squared x over cos squared x equals tan squared of x. And therefore, arguably, tan of x actually directly differentiates to 1 plus tan squared of x, not sec squared of x. But, of course, if you're familiar with your trig identities, you'll be aware that 1 plus tan squared of x is just equivalent to sec squared of x, and therefore, that is why tan of x differentiates to what it does. Some of you might have chosen to simplify that fraction a slightly different way to me, because of course that numerator looks a lot like another different trig identity. Sine squared x plus cos squared x, of course, is equal to 1. So therefore, 1 over cos squared of x is just going to be what we expect it to be. So that's another way of doing that proof. Nice. On to doing our second derivative. And therefore, we are not going to do differentiation by first principles, because doing differentiation by first principles with ln of x is just weird and horrible and silly. So therefore, instead, what we're going to do is we're going to rearrange to make x the subject to the formula, of course, getting us e to the power of y equals x. That allows us to now have something that we know how to differentiate. So we're going to differentiate both sides with respect to x. But in order to do that, we need to use implicit differentiation. So, therefore, e to the y would differentiate to e to the y if you're differentiating y's, but we're not. If we're differentiating x's, you've got to make the implicit differentiation correction of multiplying that by dy dx afterwards. And then x differentiates to just 1, so therefore this is what both sides of the equation differentiate to with respect to x. Then making dy of dx is subject to the formula by dividing both sides by e to the power of y. And then, of course, we could replace e to the y in terms of x, because wait a minute, we already know e to the y is equal to x. So boom, that is what ln of x differentiates to. 2 down, 4 to go. What does y equals a to the power of x differentiate to, where a is a positive constant? The reason we're only looking at the situation where a is a positive constant is because if a is a negative value, then you don't have a continuous curve and therefore you can't differentiate it. If you have a negative number to different powers, it fluctuates between plus and minus constantly, and therefore you don't have a continuous curve because there's no way to join up the points directly. And so therefore that's why we're only looking at this scenario. We're going to deal with this by first taking logs of both sides, specifically natural logs of both sides, ln in other words, because, of course, we now know what ln of something differentiates to using the result we just proved. So that's going to be helpful, but before we do that, differentiation, we're going to need to use log laws. That power of x inside that second log can be moved out the front, and now we're going to use differentiation with implicit differentiation to help us deal with this. Ln of y differentiates to 1 over y, and then times by dy over dx to deal with the implicit differentiation part of that. And then x ln a looks really horrible, but remember, 3 of x, 2 of x, all those sort of things are quite easy to differentiate. A number times by x just differentiates to that number. Ln of a looks scary, but a is just a constant, so ln of a is still just a number. So therefore, ln a lots of x differentiates just ln of a. So we're left with this. Again, making dy of dx is subject to the formula by timesing both sides by y, and then realizing we want to get rid of the y, but realizing we already know what y is from earlier in the question, we can say that dy over dx equals a to the power of x, lots of ln of a. There you go, something that looked really horrible, but actually the proof of the derivative of it actually isn't too bad. But what about sec of x? Well, the thing to be aware of is that sec x is secretly 1 over cos of x, or alternatively you could be viewing that as cos of x all to the power of minus 1. That means because we've got something inside something else, we can apply chain rule, and therefore let u equal cos of x, and therefore y is equal to u to the power minus 1. Differentiate both of those respective things, and then by chain rule, if you multiply those two derivatives together, you get dy dx. But that's in terms of u. But u is equal to cos of x, so undoing that substitution and then realizing the minus power means it's on the bottom of a fraction, we get sine x over cos squared of x. Again though, although that's a correct derivative, it's not the structure we're used to seeing, so we can rewrite that fraction secretly as a fraction times by another fraction. We could rewrite it as 1 over cos of x times by sine x over cos x, and the reason we're writing it in that specific way is because, of course, you'll notice 1 over cos of x is sec x, and then the other fraction is just tan x. So yes, sec of x does differentiate to sec x tan x. Wow, that's a mouthful to say. Only 2 derivatives left, cosec x and cot x. And I must admit the steps to these are fairly similar to the other 2 trig functions we've already done, so I'm going to go through them a little more quickly. Admittedly, cosec x, if you didn't want to do it by chain rule, which would be almost exactly the same as what we just did with sec of x, you could choose to do it by, admittedly, quotient rule. By viewing the top as 1. 1, of course, differentiates to 0, so as part of doing all the quotient rule stuff, you'll end up with this. which of course is just then something you can rewrite as minus 1 over sine of x times by cos x over sine of x, and that's why we end up with minus cosec x times by cot x. And what about cot x? That's very similar to tan of x derivative. All you've got to do is realize that's cos x over sine of x, do quotient rule with that, then realize that you can factorize minus 1 out of the entire numerator, and therefore, wait a minute, that stuff inside the brackets is just that trig identity again. So replace that with 1, and you end up with minus 1 over sine squared x, which of course is just minus cosec squared x. And there you go! We did all 6 derivatives. Hopefully you found that interesting, and if you did, I have some other videos on my channel that show the proof of various things in the A-levels in my Prove It series. A link to another one of that series is on the screen right now. I've also got another series called Can We Do That, where we explore some other maths areas further and take them beyond what you've seen before. Goodbye!